Hello everyone and welcome to the MetaPrep Middle School Math Club. Today we are working on problems from the 2020 Chapter Math Counts competition.
Okay.
So you have some problems you want to work on? Did you find one?
Yeah.
Which test?
I found one from the target round.
Okay, which target problem do you want to work?
It was target problem number 6.
Okay, let's see. I haven't seen these problems before, so I'm going to have to read each one as I go. 3 geometrically similar George Washington profiles are attached to the sides of a right triangle with legs of 6.2 and 9.3 centimeters. The height of each profile is equal to the length of the side to which it is attached. If the largest profile has an area of 25 square meters, what is the area of the smallest profile? Shown here shaded. Okay. It's going to be 113. So I'm going to check the answer real quick before we. Yeah, that's right. Okay. So let's talk this one through. This is an interesting problem right here. I mean, faces, like what? Faces, but they're in kind of proportion to each other. You know, what describes that proportion? I'm gonna show a similar but different problem real quick. You know, let's say that we had a right triangle. I'm gonna do simpler side lengths. I'm gonna do 2 to 3. And we can see, you know, I'm picking the same ratios that we are right here, right?
Mm-hmm.
But what is the hypotenuse of this particular right triangle?
Root 13.
Okay, yeah, 2 squared plus 3 squared is 4 plus 9, which is 13. And that is c squared, so c's got to be the square root of 13. Okay. Now, suppose I drew squares out from the sides. What do you notice about the areas of those squares?
They're all proportional.
What do you mean they're all proportional?
They like have some sort of if you like some sort of rate, like you're all like kind of similar.
Well, they are, all squares are similar to each other.
Yeah.
That's true. But tell me, what are the areas?
4, 9, and 13.
4, 9, and 13. Huh. Okay, well, okay. So, you know, that's an interpretation of the Pythagorean theorem.
Mm-hmm.
And in fact, there is a proof of the Pythagorean theorem. Maybe we'll do that sometime on a different day, but there's a proof of the Pythagorean theorem in which we do just shift these two areas around and formulate the big area out of the two smaller ones.
It's kind of weird.
It's kind of weird. It's kind of neat that it happens that way. Well, let's suppose that these were not, pardon me, trying to erase the figure. You know, I'll just leave the figure up. I'll just draw a new one. So let's do this with a shape other than a square. Let's say that we have the same exact triangle, and we put semicircles whose diameters are the sides of the triangle. So we have radii of 1, 3/2, and root 13 over 2. So let's compute the areas of these 3 semicircles instead of the squares.
Okay.
The small one is?
The smallest one is half of pi.
Wait. Oh, you're right. It's sorry. I was about to do that wrong. But you're right, 1/2 pi. Okay. And then the second one?
11 3/4 of pi.
3/2 squared pi and then times 1/2.
Yeah.
What is 3/2 squared?
9/4.
Then multiply by 1/2.
1/2, 9/8 back.
So 9/8 pi. Okay.
Excellent.
And then the last one?
Is 13/4 pi.
13/4 pi.
No,
Multiply by the half.
8.
13/8 pi. Okay. What do you notice about these three numbers?
Hmm. Wait a second. If you multiply all of them by 8, you still get the 4, 9, 13.
Very good. That's one way to notice it. Yeah, they are still in that 4, 9, 13 proportion. And so the sum of the first two still equals the third.
Hmm.
Is that always going to happen?
Maybe. I don't know.
Let's do one. So the semicircle one, that one was a little bit funny. Oops, I meant to give us more pages to work on. Let's do that for one more triangle. And we'll use the same side lengths. And this time I'm going to put equilateral triangles. Do you know the formula for the area of an equilateral triangle?
A squared times √3 divided by 4.
Okay. This time I'm not actually going to compute the areas. I'm just going to write the formulas down. We would have 2 squared times √3 over 4. 3 squared times √3 over 4.
Wait, this is already familiar. It's already just 4, 9, 13 again.
Yeah. Yes. And can you come up with some explanation as to, what is actually going on? Is it always going to be this way? Is it going to be this way with the George Washington faces?
Yes.
How come?
I don't know exactly how to describe it.
It's all right. Do your best.
It has something to do with like the formula. It's just you have to.
What happens in each formula?
You have to square it.
Okay, you have to square a dimension. Yeah. And we could say, it's always two-dimensional. Each one of these, they're all two-dimensional. And we are stretching by proportion in one direction and stretching by proportion in another direction. And so if you have an equation like 2 squared plus 3 squared equals √13 squared, a squared plus b squared equals c squared, whatever it is that you multiply in, whatever kind of proportion or constant or other thing that you do to get an area,
it's gonna remain the same.
Yeah, the fact that the sum of the two smaller ones equals the bigger one remains the same.
That's weird.
It's weird. It's cool. It's weird. And they gave us the weirdest version of this problem I've ever seen. I've seen this numerous times in different ways, but I've never seen it with George Washington profiles.
I don't see George Washington.
Let's see. If I draw an eye right there, Draw a mouth. Do you see it right there?
Oh, now I see it.
Maybe we can give him a beard.
I'm not sure he had a beard.
No, he didn't. I just thought it would be easier to see the face that way. All right. So what's our answer here? I said it earlier, but I'm going to let you compute it yourself now that you've conceptualized the idea.
I think I heard you say 100 over 13.
Did I? I'll let you
I don't know.
find out.
Wait a second.
So what fraction of the area of the large one is the smaller one?
What fraction? 6 point. No. Wait. So the side length is 6.2, and then the hypotenuse is root 124.73.
I don't know what that is. We know that the biggest profile has an area of 25 square centimeters.
Yeah.
And we want to know the smallest one. And we know the smallest one plus the second smallest one equals the biggest one. And they are similar. Just like the triangles, just like the semicircles, just like the squares. So in what proportion are they?
Wait, so we just find two numbers that add up to 25.
How would we do that?
They have to be in the same proportion. I'm not sure.
Well, if so a few ways we can do this. Let's suppose this first one is 4 parts. I like to think of ratios sometimes in terms of 4 parts of this, 9 parts of that, and then 13 parts of something. Oh, it's all the same thing. So the first one we can think of as 4 times n is its area. So the area of the second one would be?
9n.
And the third one?
13n.
13n. But what's 13n equal to?
4n plus 9n.
In the problem, what else?
Oh. Aren't they? Wait.
We have two ways to express the same quantity.
Yeah.
And that gives us an equation. I call this the fundamental principle of algebraic problem solving.
Mm-hmm.
Find two ways to express the same quantity, equate them. What does 13n represent?
The biggest one
Right. And what are we told about that one in the problem?
is 25.
Right. So we have two ways to express the area of the biggest one. What does that mean?
We could write an equation.
What equation? What is equal to what?
What is equal to 1?
What is
N?
equal? What are the two expressions for the area?
For the area.
Area of the largest profile. We have two ways to express that area. What does the problem say it is?
25.
25. Okay. What do we say it is in our?
The two smallest ones added together.
Which is?
4n and 9n.
Which is?
13n.
Right. So what is n?
N is 25 divided by 13.
That's right. So what is the area of the smallest profile?
If n is 25 out of 13, is it 50 out of 13?
You're warm.
Wait, 100 divided by 13.
Yes.
Oh.
Yeah. Area of the smallest one is 4n. Area of the middle one is 9n. Area of the large one, 13n.
Mm-hmm.
Can you tell me why?
Because you just expressed it in a different way.
Well, we have a ratio of 2 to 3 of one of their dimensions. That means that the ratio of their areas is
the same.
Not 2 to 3. What was the ratio of the areas? Squared, right. It's that ratio squared. Exactly. Because we're stretching in 2 dimensions, not just one.
Mm-hmm.
3 halves times 3 halves is 9/4.
Cool.
Cool. You like that one?
Yeah. I had no clue what the answer was.
Yeah, it is a goofy problem until you've done a bit of until you've done similarity to a pretty abstract degree. That's going to be a weird one. But I can tell that you mentioned that one right when we sat down, so I can tell that you remembered that one was a weird one for you. Are there any of these other target round problems that you want to take a look at?
Let's see. What about the one before that, number 5?
Okay. Oddie, subi, multi, and divi, addition, subtraction, multiplication, division, are given two distinct non-zero numbers. Oddie adds the two numbers, subi subtracts the lesser from the greater, multi multiplies the two numbers, divi divides the greater number by the lesser. The result obtained by addie, multi, and divi are the same. What is subi's result? Okay. So we've got two numbers. I'm going to give them names. X and Y. We add X plus Y. We get X times Y. And I'll assume that X is greater than Y because it doesn't matter. We usually, by the way, have you heard the phrase without loss of generality?
No.
You will hear that phrase in mathematics. You'll start hearing it a lot. Without loss of generality means we are going to work one version of this problem where x is greater than y. And the reason we can get away with working just one version, working it this way, is because all the other versions are really the same.
Oh.
It just means all the cases are symmetric. And so we don't lose any generality of the problem by doing it this way. So we have these three pieces that we have equated right here. With an equation chain like this, what can we do?
Try to solve it.
But how do we go about it? I'm going to let you think for a moment. I need to let a pet out. So we have these three pieces. They're all equated, three expressions equated. I like to focus in on what's easiest to work with. And I think two of these three they're more alike than the other one.
Mm-hmm.
Which two are more alike?
X times y equals y divided by x divided by y.
I think that those look like the easiest ones to get started with. So we're talking about non-zero numbers, distinct non-zero numbers. What can we do with that equation to make life a little easier?
Simplify.
Simplify? How do we simplify?
Multiply both sides by y.
Okay. If we multiply both sides by y, we get xy squared equals x.
Doesn't it divide both sides by x, which leaves us with y squared equals 1.
Since x is non-zero, we can divide by x, and we have y squared is 1. So y equals, let's see, can it be negative? Right now
Or
it's
positive.
They're non-zero numbers. Huh. Guess we don't know for sure yet, but we know that x plus y equals xy. So we'll take on that part next. And I'm gonna rewrite it like this, and maybe I'll come back and tell you why I rewrote it like that, or maybe become clear. Now that's a different looking equation. Oh, but you know what? We already have information, don't we?
Mm-hmm.
It's not really a two-variable equation anymore.
So we could just test for both ways, right?
Might as well. I think so. Why not?
So x plus. In one way, x is 0. The other way, x is 1/2.
In the first way, I did not get x is 0. Right here?
Mm-hmm.
X equals x plus 1, is that what you got?
Yeah.
Well, if we subtract x from both sides, what do we get?
From both sides, we get 0 equals 1.
That's funny. You're telling me that 0 equals 1?
It's not possible then.
It's not possible. Yeah, that's a contradiction. 0 is not 1.
0 is not 1. So that one's not possible, so it is 1.
Indeed.
X equals -1 and x equals 1/2.
Yeah. X equals 1/2, y equals -1.
So
and
the answer
so
is 1/2. 1 and 1/2.
yeah, I agree with you. I'm gonna always want to check. Yep, 3/2 is the answer.
Okay. That was also interesting.
Good. Now, what did you get out of this one? What was the interesting thing about this one?
You had to like play around with the numbers a little bit.
Yeah, of course, you need to, for a lot of people, just naming the numbers to get started, that's important. But, with an equation chain that has, multiple pieces like this, finding a good place to start, finding a good place to work. And, sometimes you have clues, sometimes you just have to test things out. But, x, y equals x over y, you've got multiplication and division. And really, in a sense, those are the same operation. You just, when you divide, you multiply by a reciprocal. So those were a lot easier to manipulate to get into a productive place. Okay, that's another problem you'd like to take a look at.
Okay, let's see. Let's see about the sprint.
Okay, we are working the 2020 Chapter Math Counts test. We're going to take a look at some problems from the sprint round now.
What is number 28?
Well, let's take a peek. In the figure, a kite with 2 right angles is circumscribed by a circle. Turns out every kite with 2 right angles can be circumscribed by a circle. The circle is then circumscribed by a square such that the diagonals of the kite are parallel to the sides of the square. Okay, the longer sides of the kite each have length x meters. The sides of the kite are divided into 3 regions. The sides of the kite divide the square into 3 regions, shaded dark gray, white, and light gray, with each region of area 2 meters squared. Oh, so the areas of the regions are exactly the same. And then we want to know, essentially want to know the side length, the square of the side length, the big side length of the kite. Interesting. Okay. Well, what do we know? Let's be investigative. Let's be investigators. Be Sherlock Holmes here, and we need information. What information is the easiest to get started with?
Maybe the fact that they have all 3 areas have the same, all 3 of the spaces have the same area.
Okay, what does that mean?
But I mean, the ones on the side are definitely equal, but then the center one is somehow equal to the other one.
What is some simple way to use what we know? We have areas of 2 and
Okay,
2.
so then the area of the big square is 6.
Yes.
And then root 6.
Yes. Yeah, the area of the square is 6, so its side length is root 6.
Mhm.
Where else is that side length?
The hypotenuse of each right triangle.
Yeah, it's the big diagonal of the kite. And if we draw that in, it is the hypotenuse of each of 2 right triangles. So root 6. Okay.
Wait. And then the altitude to that thingy. Wait. I mean, I can find out the diagonal.
Oh yeah?
Wait, so I know half the diagonal is root 1 out of 6, I think. Because root 1 out of 6 times root 6 is 1, because it's half of that. So then you multiply that by 2.
So what's the area of each one of these right triangles?
1.
Okay. The area is 1. So what does that mean? So I just drew one of these right triangles out over to the side.
So x times question mark equals 1, 2.
Yeah, let's give that question mark a better name. X times y equals what?
1.
Is it 1?
Wait. 2.
Yeah, it's 2 because x times y over 2 is the area, and that area is 1. So x times y equals 2. What else do we know about x and y?
X plus y equals 6. No, x squared plus y squared equals 6.
Yes. Yeah. Mm-hmm. Now, we have a system of equations.
Yeah.
And seem to have a momentary hesitation solving it, which I can understand. Doesn't look like the average system of equations. I wonder what we can do with this.
I mean, you can't really put those two together.
So there are different strategies here. Let's talk about 2 strategies for maybe going after this. Now, one of the things that we can do with any system of equations, actually, you tell me, when you solve simpler equations, let's say linear equations, what strategies do you use?
Where now I know how to solve it.
Do you?
Yeah.
Just by me asking you, what strategies do you know?
Yeah, because if you multiply both sides of the first equation by 2, and then you add them together, isn't it just like a quadratic?
Okay, now this is interesting. This is not even one of the places I was going, but yeah, you can multiply the first one by 2, then add the equations together. And we get this, which means that x plus y squared is 10.
So x plus y equals root 10.
Okay. Getting warmer. How else could we combine those equations?
Then I'm not sure where to go.
We made x squared plus 2xy plus y squared, which turned out to be a useful expression that you're familiar with. You knew it was the square of a binomial.
Mm-hmm.
Is there any other useful, familiar expression that you can craft out of these two?
Not really off the top of my head.
I'm going to say look for something very, very similar. You have x plus y squared, which gives x squared plus 2xy plus y squared. You have the sum of the squares, and you have a product. And you manipulated the amount of that product that you wanted in order to put it together. And you made x plus y squared. What else could you have done with the xy to come up with something that,
You could have subtracted it.
okay, what can we get?
X minus y squared equals 2. So x minus y equals root 2.
Equals the square root of 2?
Yeah. So then 2x equals root 10 plus root 2.
Okay. And then we want x squared.
Yeah. Equals 12 over 4. So x squared equals 3. Wait, no. No, it's not. 3 plus root 5. A plus b is 8.
And that is our answer. Actually, I just said that because I agree with you. I'm going to look it up because I always should, just in case. Yes, 8 is the answer. Awesome.
That was interesting.
That was interesting. And I'll go ahead and tell you this. What you just did, this, like, you'll see this. You'll see it a lot of times. X times y and x plus y are known as symmetric sums. Sometimes you will see them given other names, elementary symmetric sums or Euler sums. Have you heard of Leonard Euler?
I've heard. No.
You will see it.
Oh, him.
Him. Okay, yeah. So you have seen this. Yeah. That's pronounced Euler. You know,
Euler.
it looks like you want to call it Euler at first, right? But it's Euler.
Yeah.
And yeah.
Euler's number is like 2.18 something.
2.718, give or take.
Yeah.
Yes, that's the same Leonard Euler. And x plus y and x minus y sometimes, or sorry, x plus y and x times y are sometimes called Eulerian sums or Euler sums, and they're symmetric, and so they can be manipulated in in nicer ways. And you'll learn to do that a lot. Like this will become second nature after a while. I just want to point out though that there were other ways we could have tackled the system. Really and truly, Substitution. Every equation is a potential substitution equation.
It looked kind of weird to substitute it in.
It does look kind of weird, but you will get used to it. I mean, like that, it's not the craziest thing. It's not the easiest thing in the world. It's certainly not the craziest either.
Yeah.
One nice thing about the substitution is you get like x squared plus 4 over x squared equals 6. And you're very quickly thinking about solving for x squared once you multiply out a denominator, right? And so you're solving for x squared as if this were x squared were the root of a quadratic.
Oh yeah, that makes sense too.
And so substitution is possible. And then I was thinking of another. I was thinking square the first equation, and then you could use the second equation as a substitution into it, because now you're comparing apples to apples, right?
Yeah.
Lots
Substitution.
of good paths to that one.
Mhm.
Okay. What's another one you want to take a look at?
Let's see. Let's just do the last one. Number 30.
I like the way you're challenging yourself. Okay, triangle ABC has vertices. A is at 0, 5. B is at 12, 0. C is the origin. The image when ABC is rotated clockwise about the origin. The image when triangle ABC is rotated clockwise about the origin is triangle A prime, B prime, C prime with vertex 3, 4, 8. Okay, so this, okay, so if we follow any one point, rotation preserves distance. And so we wind up with this new point, A prime, which is also 5 units from the origin. It is at the point 3, 4. What fraction of the area of triangle A prime, B prime, C prime is below the x-axis? Okay. Fraction of the area. Okay, so we have rotated this enough. The A prime is here, and then the angle is preserved. So B prime is going to be down here somewhere. And then C prime, we're rotating around C. So C prime is at C. So we're looking at this blue triangle right here. And we want to know what fraction of the original area. What is the area of the original triangle?
30.
Product of the legs divided by 2 is 30. Okay. And now we want to know the area right there. And I'm going to go ahead and say this, whether or not you need to do this. This is a point at which I might redraw the diagram and, focus more bigly. So A prime is there. Do we need B prime? There's probably different ways to work this problem. We have a right angle in case we need it. That's still 5. That's still 12. That length is still 13. And we want to know this gray area right here. What would help us find that out?
By finding the height and the base.
Okay, a base and a height. What do you mean when you say, are you thinking of a specific base and height?
Maybe the base on the x-axis.
Okay, I'll call that point D, where the hypotenuse crosses the x-axis. So you're thinking about C prime D or CD, right?
Yeah.
Okay. What is the height?
The height? A prime to some point on the x-axis, creating a right angle.
Yeah, by the way, I actually kind of drew this wrong. I made it like it was 4-3. Should be slanted a little more up like that. Probably. But hopefully, we'll get the right answer in the numbers one way or another, even if I botched the drawing a little bit. But we can tell the height, right? What is A prime to the x-axis? What's that distance?
Isn't it just 3? No, it's 4. It's just
4, right? Yep. Which means we just want twice the base. We need to know the base, so we need to know what coordinates D is at. What are the coordinates of D? We know the y coordinates here. We need to know the x coordinate of D. And D is on this hypotenuse.
There's a right triangle in that because it's 3, 4, 5. So 3, 4, 5.
So we've got this line, A prime, B prime. The hypotenuse is on. If we understood that line, we could find D pretty easily.
Yeah.
I'm just going to call its coordinates x0. It's on the line with A prime and B prime. We know A prime. Do we know B prime?
No.
Well, we know that B is distance 12 from the origin, and then we rotated it clockwise. B to B prime. And Well, do you know what facts do you know about lines? I asked that question because we have a piece of information that we haven't used.
Wait.
Sometimes it's worth asking, what information have I not used in a problem? We have a piece of information here we haven't made use of, and that's that we have this right angle at C. What do you know about lines that meet at a right angle?
I don't know. I'm not sure. I don't know.
It's okay. Have you ever heard that when two lines meet at a right angle, if neither of them is vertical or horizontal, then the product of their slopes is something special.
It's -1.
It's -1, right? Do you know why it would be -1?
No.
I'll go ahead and tell you intuitively. We'll prove that one day. We'll go over that. But intuitively, you're replacing rise with run and run with rise. And one of them is positive and the other one is negative. One of the slopes is clearly going up, the other one's clearly going down from the point at which they meet. So if the line from the origin to A prime, C to A prime, is it's got slope 3, 4, so 4/3 is the slope. So what is the slope of the other one?
It's just -3/4.
Right. In fact, that line, it goes through the origin, so it's just y equals -3/4 x. But it's also distance 12. You know, we could say that the coordinates here are b -3/4 b. That makes a right triangle with side lengths that are in proportion 3 to 4. So its distance from the origin, it's like a 3, 4, 5 triangle. It's 5/4 b. That's got to equal 12. I want to make sure that you're comfortable with that before we move on, because that is probably the toughest detail piece.
Yeah. 5/4 of b equals 12. Okay.
So b is 48/5. And we have the x and y coordinates.
Mm-hmm.
So now we need a line that is a prime, b prime. We need how do we get the equation of that line?
Y coordinate of one of them minus the y coordinate of the other one divided by x coordinate, x coordinate.
What does that give us when we do y minus y?
The slope.
Right. That's our rise over run. Oh my goodness. Y equals -56/33 times x. How do we get the plus something here?
That's the y-intercept.
Yeah. What do we have that we can get that from?
Oh, we have the slope, so you could just use 3 and 4 and then.
Right, we can plug in the 0.34. Okay. So now we need the point with y coordinate 0.
So 100. Huh.
Wow. If this weren't problem 30, I'd be worried about my arithmetic. There we have it, 75 over 14.
Okay.
That should be the length of the base. So the area above the curve would then be 75 sevenths, and that would be out of 30. 75 over 210 divided by 15, 5/14ths, really?
That sounds weird. That number is kind of weird.
I just looked over and the answer is 9/14ths, and I realized that I was misreading. I did above the axis. That's one reason it's good. And you know what? This is always a habit that I would make anytime I was taking, whether it's an important test or I'm doing work. Always right when you come up with a computation, check to make sure that it matches what it is that you need. So in this case, it's below, but we came up with above 5/14, so obviously below would be, subtract that from 1, and we get 9/14. That is the correct answer. So, let's talk through this one. This is the last sprint round problem. Obviously, it's a challenging one.
The hardest one.
It's the hardest one, and it's even for students who have done this for a couple of years, this one is a hard one to do quickly. Right? You can't do something quickly till you know it real well. So let's talk this one through and tell me what it is that you learned or what it is that we needed to do to solve this one.
You needed to find the area above the triangle when it got rotated.
Okay.
But you needed to find the height of it, and then you also need to find the base of that part.
Okay, so even like thinking, I would call this backward thinking. A lot of times what we do in geometry is we think forward if we have enough information, but a lot of times we go, what is it we want? We want an area. How do we get an area? Oh, we do base times height. And then we look, we go, okay, where's a base and where's a height? So we identified this base along the x-axis and this height. And then which one of those was easier?
The height.
The height. Yeah, we already had the height really within the coordinates. 4. So we just needed the base, and that was the complicated one. What do we do to get that base?
The base, you have to figure out where it was the x-intercept of the line that contained A prime and B prime, which you had to find out through the fact that it was a right triangle and the lines were perpendicular. The two legs were perpendicular.
Good explanation. Good. I can see that you absorbed everything. Well, excellent. Well, I think this seems like this is a good stopping point.